We'll consider the example in Section 4 of the SOP tutorial handout on supply chain agility. This involves the aggregate plan for product A. And I have my solution for that aggregate plan open, and we can see the original demand numbers in this particular example. I'm going to copy these demand numbers, the original ones, out to the right for reference, and then enter a number in I2 that represents a potential change in monthly demand. Right now I have 0 as the monthly change, but I'm going to add a formula on line 2 that is the original demand plus the change. That way we can change the demand by month by just changing one cell when we want to do this analysis in a few minutes. As we can see, the total sales for the 6-month period are $18,377, and the total cost is $1,578,130. The example in the tutorial considers 3 different cases for potential changes in demand, and these are considered in the template. We consider changes in monthly demand of -50, 0, which is just the original demand, and 50. And eventually we'll consider that each of these have a probability of 1/3. So if we look at the 9 different scenarios we're going to consider what happens if demand ends up being one of these 3 cases with no buffers, inventory, or capacity. What if demand ends up being in these cases with a 300-unit inventory buffer, or what about a 50-unit capacity buffer? If there's no change in monthly demand, the sales over the 6-month period are going to be $18,377. If there's a 50-unit decrease in monthly demand, we're going to lose 6 times 50 units over the 6 months, so it'll be $18,377 minus 6 times 50. If demand increases by 50 units per month, in the last 2 scenarios, we're going to assume that the buffers would allow us the flexibility to increase our sales by 50 units per month. So we would take $18,377 and add 6 times 50, or 300. In this one scenario, where demand actually increases but we have no buffer, we're going to assume in this example that within that 6 months we're not able to respond, so we would still just simply sell the original amount of the demand. As an opportunity cost, we'll consider the lost sales that we would incur in that case. This example assumes a sales price of $150 for this item, and so the total revenue would be the units sold times the sales price. The total cost we need to get from the model in all of these cases. We need to go back to the aggregate planning model. This is the original model. I'm going to copy this model to create a model that has a 300-unit inventory buffer. The solver constraint is already built into the model, so if we change the inventory buffer minimum to 300 and resolve, we'll get a new plan for the cost involved in maintaining the inventory buffer. With no change in demand, the cost is $1,615,843. I can put in the cost for the original scenario of $1,578,130. Now we create a model with a capacity buffer. The solver constraint is already set up, so if we change the minimum capacity buffer to 50 and solve, we get the new cost with no change in demand, $1,599,210. Now we need to adjust these models in the case where there's a monthly change in demand of -50. Without any buffers, if we change demand by -50 each month, we see that the total goes down to 18,077. We don't resolve in this case because we're not assuming that we're able to change this plan for labor and overtime within this period of time. So our cost changes to $1,583,380. The reason the cost is different is because we're holding more inventory now that we're not selling additional inventory. What about the inventory buffer model? If we change this to -50, total sales goes down to 18,077. Our total cost is now $1,621,093. And then we do the same for the capacity buffer model. Change this by -50. And we observe that our total cost is $1,604,460. So we've handled the cases where we have a monthly change of -50 units. Now let's think about what happens if demand increases by 50 per month and we have these two buffers. A buffer of 300 is enough to withstand an increase in demand of 50 per month and not lose any sales. So let's look at this in the inventory buffer model. Instead of -50, we look at sales a change of +50. We notice one thing, there's no excess capacity. We didn't have a capacity buffer. We notice that our ending inventory is always positive. And we've always had enough sales, units on hand, to meet demand. We know that because our ending inventory is positive. We end up with 0 inventory because we've used up our buffer to satisfy the extra 50 units of demand. Our cost has changed to $1,610,593. What about the capacity buffer? This is a little bit trickier. What about a change of 50 units per month? If we go down and observe what happens in the model, once we put in the 50 units a month, we see that we've got excess capacity of 50, and now we've got a negative inventory in month 1 and an inventory that approaches negative 300 by month 6. What we've got to do is essentially use up this excess capacity to change our units produced. We'll just do this in this case manually. We're not going to resolve. Instead of resolving and changing our plan, we're going to use the production capacity buffer to increase by 50 units a month. And then we'll see our deficit in inventory go away once we do that. Because we increased production manually, we no longer have excess capacity, even though we started with it. But we're okay in terms of ending inventory, not going negative. Our cost is now $1,605,210. Some materials cost and unit holding cost have changed. In the case of an increase in demand of 50, the problem with having no buffer is we're not able to change our production, and we don't have inventory to satisfy the original demand. So our cost is still the same as the original scenario, at least the cost from the model. So in every scenario, our gross margin is total revenue minus total cost. So we calculate this in all scenarios. There's one scenario here where we need to consider lost sales. And it's this scenario where we have no buffers, but demand has increased by 50 units per month. So we think about our unit gross margin in this scenario. If we look at our original model and look at the original sales, our unit cost was $86.35. So our unit gross margin is $150 minus $86.35. We're considering here an opportunity cost factor of 1.5, which means that we're assuming that if we lose a sale, we lose another 1/2 of a sale later on because of the lost goodwill with customers. We would have total lost sales of 300 over the 6 months. So we're assuming a lost gross margin here of $63.65 times 1.5 times 300, which means our effective gross margin is the gross margin we actually have from sales minus the lost gross margin. Let's enter these numbers in the table above. For negative 50, we have these 3 numbers. For a positive 50 change, for a 0 change, we have these 3 gross margins. And then for changes of 50 units, for the inventory buffer, we reference these numbers, but for the case of no buffers, we have the effective gross margin, $1,149,778. In each case, the expected gross margin is the probability times